Welcome, students. Let's dive right into today's class. We are tackling a super exciting chapter on the effects of electric current. We interact with electricity every single day, right? From the lights above us to the phones in our hands. But today, we're going to look under the hood. We're going to truly understand what actually happens when that current flows through a wire. Here is our roadmap for today's explainer. We'll be moving through 5 key topics: energy and electric circuits, Joule's law of heating, heating appliances and units, safety focusing on fuses and MCBs, and finally, the magnetic effects of current. Let's get started.
Section 1. Energy and electric circuits, understanding the basics.
Now, think back to what you've learned in earlier classes. You already know that static electricity involves transferring negatively charged particles. But what happens when we set up a continuous path? Take a look at the basic circuit components here. We've got our connecting wires, an electrical resistance, a voltmeter, and an ammeter. If a charge, let's just call it Q, flows from point A to point B, work absolutely has to be done. So where does the energy to do that work come from? Well, it comes from the electric cell on the left. That cell provides the energy to physically push that charge right through the resistance.
So I want you to really use your brain power for a second here. The cell is continuously providing energy to the resistor to keep that current flowing. But as we know from physics, energy cannot just disappear. So what exactly happens to all that electrical energy provided by the cell once it hits the resistor? The answer is quite literally a warm one. That energy is converted into heat energy, and the temperature of the resistor actually goes up.
Which brings us to Section 2, Joule's law of heating, deriving the formula.
Imagine we're standing at the chalkboard together. Let's build this equation step by step. Step 1. We know that electrical power, which is P, equals the potential difference, V sub AB, multiplied by the current, I. Step 2. Heat generated, or H, is simply that power applied over a specific amount of time, T. So heat equals P times T. That means heat equals V sub AB times I times T. Now step 3. Let's bring in our old friend Ohm's law, which tells us that V sub AB is equal to I times R. Finally, step 4. When we substitute Ohm's law right into our heat equation, we get I times R times I times T. Simplify that down, and we arrive at our final result. Heat equals I squared times R times T. This beautiful, elegant equation is what we call Joule's law of heating.
Now, the really crucial piece here is understanding exactly how we measure this energy transfer. The standard unit of electrical power is the watt. Notice the definition. 1 watt is equal to 1 volt multiplied by 1 ampere. If we think about it in terms of actual work being done, 1 watt is exactly equal to 1 joule of energy being transferred in 1 single second. Basically, it tells us how incredibly fast that electrical energy is being consumed or converted into heat.
Moving on to Section 3, heating appliances and units, physics in our homes.
Okay, so now that we've totally mastered the theory, how do we actually use this heating effect to our advantage in daily life? Let's compare the equipment shown here. Things like water boilers and electric cookers need to generate a massive amount of heat. So, on the left, we use electrical conductors with much higher resistivity, like a coiled coil made of an alloy called nichrome. That high resistance intentionally generates the heat we need to cook our food. But check out the right side, an electric bulb. Here, a tungsten wire is used. When current flows, this tungsten wire gets so hot, we are talking nearly 3,400 degrees Celsius, that it actually emits light. It's the exact same physical principle. Joule's heating gives us both the heat to cook our dinner and the light to read our books.
Now, have you ever actually looked at the monthly electricity bill your family gets? The usage is always specified in units, but what exactly is a single unit? In practice, a single watt is a remarkably small measure, so we use 1 kilowatt hour to measure larger amounts of electrical energy. Let's do the math together. 1 kilowatt is 1,000 watts, 1 hour is 3,600 seconds. Multiply those together, and 1 kilowatt hour equals a whopping 3.6 million joules. So, next time your bill says you used 1 unit of electricity, you'll know you actually consumed 3.6 times 10 to the power of 6 joules of electrical energy. Pretty amazing, right?
Section 4, Safety. Fuses and MCBs, preventing electrical mishaps. With literal millions of joules of energy flowing through the walls of our homes, things can occasionally go wrong. Sometimes the plastic coating on the live and neutral wires can wear away or give out. That causes the 2 wires to touch, creating a massive amount of heat. To prevent absolute disasters like fires from short circuits or overloading, we absolutely have to use protective devices. Let's compare the 2 main types. The traditional fuse wire is designed with a very specific melting point. As soon as a dangerously high current flows through it, this fuse wire simply melts, instantly breaking the circuit. On the flip side, nowadays we frequently use miniature circuit breakers, or MCBs. When the current spikes too high, this switch just opens up suddenly and stops the current dead in its tracks.
And here are the actual devices keeping you safe every day. On the left, we have various types of traditional fuses. Some are ceramic, some are glass. The catch with these is that they have to be physically replaced once the wire inside them melts. But on the right, you see modern MCB switches. The totally brilliant thing about an MCB is that you never need to replace a melted wire. Once you fix the electrical fault in your equipment, you literally just flip the switch back up to restore the power. It's a real game changer for home safety.
Finally, Section 5, Magnetic Effects of Current, a new connection.
Up to this point in the lesson, we've focused entirely on how electric current generates heat. And for a really long time, people actually thought electricity and magnetism were completely separate phenomena. But that all changed because of Hans Christian Ørsted. In the year 1820, this brilliant 19th century scientist made a simple but completely world-altering observation. He noticed that when a current passes through a metal wire, a magnetic needle placed near that wire actually turns. He proved once and for all that electricity and magnetism are intimately linked. It was such a big deal that the unit of intensity of a magnetic field is actually called the Ørsted in his honor.
To really grasp Ørsted's discovery, just imagine passing a thick copper wire straight through a piece of cardboard and then sprinkling iron filings all over that cardboard. When you turn the current on, a magnetic field is instantly produced, and those iron filings beautifully arrange themselves in perfect concentric circles around the wire. It's like magic, but it's physics. The rules here are incredibly clear. First, a straight current-carrying conductor creates a magnetic field. Second, if you increase the current, the intensity of that magnetic field increases right along with it. And third, as the distance from the wire increases, the magnetic field decreases. That is exactly why those concentric circles become larger and much more spread out the further you get from the center.
So we've proven that an electric current can physically move a magnetic needle. This is incredibly exciting, and it begs a massive question for us to ponder. If electricity can create mechanical movement through magnetism, how can we harness this effect to build the electric motors that run our fans, or the giant generators that power our entire cities? I really want you to think deeply about that, because it forms the entire basis of our next lesson. Keep that curiosity alive, and I will see you in the next explainer.